So we're going to talk about computer hardware, and we're going to talk about resistors, transistors, and how to use those to make gates, like NAND gates and NOR gates, and decoders, and then take those parts to make additional parts. So I know some of you have an electrical background. Do these symbols and this symbol look familiar? No? Okay, so this symbol is a resistor, and what its goal is, and we talked about electricity last week, what its goal is if electricity is trying to come down this pad, it will resist it. It will make it more difficult for it to go through. And the resistors have different values on them. Has anyone seen this piece of electronics? So this part right here is a, okay, so what? Transistor. You remember what a transistor does?
It has an input and output.
What's that?
It has an input and output and a switch where it decides.
It has an input, which is a switch that you can turn on or off. But if you turn it on or turn it off, you remember what happens? It can block the electricity. So basically, electricity that's coming down this way and is going to ground, we can turn the electricity on here, which will allow it to pass through. If we shut the electricity off here, it's kind of like we've turned the resistance up to infinity. Nothing can get through. So they call it a transistor, so it's like a resistor, but it transmits current. So if we wire a transistor and a resistor together like this, what do we have? Well, we have a battery source coming in and a ground where it might be trying to get to. And for this presentation, our inputs are on the left and our outputs will be on the right. Okay. So if you apply electricity to the transistor, what you're doing is allowing the electricity that's coming through here to pass through to ground. And since there's less resistance going here as opposed to going this way, no electricity will go out. So, by applying electricity here, the result is no electricity comes out of here. Right? And so the transistor is an interesting, it's an interesting invention. It was invented here in New Jersey at Bell Laboratories. And this is actually the water tower at Bell Laboratories down on one of their buildings by the Garden State Parkway on 114th, exit 114. And this transistor, this is actually a water tower, but this is what a transistor looked like when they originally made them. They don't look like that now. But there was the switch, and then the input and the output. So it's a three-legged, kind of like a cereal bowl on three legs. But it's an interesting, water tower that Bell Labs has. And there was actually a little bit of a funny story that the water tower is very far away. It's maybe about 2 or 3 football fields away from the building. And there's a long road that people, when they come home from lunch, since there's no police on the road, they try to get their car up to 100 miles an hour before the road ends. And one day, someone didn't slow down and went into, there's a lake there, so drove into the lake. So this property has, this is where the transistor was invented, and also the Big Bang Theory, some data was collected there. And then we also had the guy who drove into the lake, so we had like all types of people working there. So I had a lot of fun working there. And I guess I drank a lot of water out of that tower. Okay, so this is the picture of the transistor. When we input a 1, the result is a 0 goes out, because we allowed the current to flow through. So since this is time consuming to draw, we're going to draw it this way. This means a piece of electronics that if you put a 1 here, a 0 comes out. And then the same thing here, if you put a 0 here, what happens? Well, by applying a 0 to the transistor, you're blocking current from flowing through, therefore it has no choice but to go through the resistor and out. And so this cartoon really means this. And we're going to say that if we put no current here, then current will come out of here. So I wanted to show you the inside of it because I don't want you to think there's magic going on. I don't want you to think that if you put electricity, well, this one, if you put electricity here and it doesn't come out, you might think you're going to start a fire. right? You're pushing electricity into something and it's not coming out. It's actually coming through the top, and the electricity from here are merging and going to ground. It's going to a place that's not in the picture. And then this one, if you put no electricity on and electricity comes out, you might ask, where did the electricity come from? And it comes from the battery that's connected to this. So there's no magic here. So this is called a NOT gate, meaning whatever value you put on it, the opposite is what comes out. So the word not, means the opposite. You're going to somebody's house, or you're not going to somebody's house, right? So that's called a NOT gate. Now, what if we decided to add an additional transistor? What if we decided to have two transistors in parallel? Well, now we have two inputs and one output. So what happens here? Well, if the electricity, if this is turned on and this is turned on, then we've allowed, it's like we've opened the door, or we're going to start calling these gates. It's a gate where we can open and close it. We've opened the door for the current to get to the bottom. Therefore, no current comes out of here. So if both inputs are on, no current comes out. But what if one of them is on and one of them is off, or both are off? What would happen? If they're off, what that means is electricity either can't get through this one or can't get through this one. If either one is off, if there's any zero on the two inputs, then the output will... Oh, these should be zeros. Sorry about that. So if we... No, wait, no, I'm sorry. This is correct. So if we were to give this thing a name, what would its name be? Well, it looks like the outputs, as long as something is a 0, the output is a 1. But if they're both 1s, then the output is 0. So if you were to give this a name in English, what would you call it? You kind of have to like put a whole sentence, like if both are on, then the output's off, which would then imply all other cases the output would be on. So we're going to use the symbol, this symbol with a circle in front of it. And going forward, anytime we see a circle, that now is the NOT gate we just talked about. Okay. Now suppose we had a transistor and a second transistor, but instead of being in parallel with each other, they were side by side. Okay? Suppose they were side by side. Then the electricity can get to ground one of two ways, one or the other. It could go down this path, or it can go down this path. If it can get there either way, then nothing will come out of here. So if I shut one off or both of them off, then electricity has no choice but to go out. So this is called the, so this would be the output of this gate. And if anything is on, if any of the inputs on, either one, the output is a 1. So, so this has the behavior that if any of them are on, any one of the inputs are on, the output is off. So you might say something like, you might call this thing anything on means output's off or something like that. What we're going to end up calling this is the NOT, the opposite of an OR. Because if we change these from 0 to 1, 1, 1, then it would be like an OR gate. Okay, now that we've made these parts, we can start plugging these parts into each other, right? So what we can do is we can take a NOT OR gate and take its output and run it into a NOT gate, and now we've made an OR gate. We can take a NOT AND gate, and we can build an AND gate by running its output into a NOT gate. And then that would be, this will be the symbol for an AND gate, meaning, so it's the same AND symbol without the circle in front of it. And then if we, what we're going to need in a little while, we're going to have, if we need more inputs than 2, we can just start plugging them into each other. We can take 2 inputs and take the result of that and plug that into another one and so on. We could build a cascade. The other thing we could do, and this will be an exercise for us to do, is we can just add another transistor. Have 3 in a row or 4 in a row. If we know in advance that we need more inputs, we could also do that. Okay. So the next piece of hardware that we're going to use is a decoder. So like I said, everything on the left side is our inputs, and everything on the right side is our outputs. Okay, so this has two inputs. So if we have two inputs and we can turn them to 0 or 1, then we have four possible ways of doing it. We can do 0, 0, 0, 1, 1, 1, 0, and 1, 1. And let's just follow the logic here. What happens? So if the input, so we're saying that the red line is a 1 and the green line is 0. So this 0 goes into this input and gets converted to a 1, comes into here. This 1 goes into this NOT gate and gets converted into a 0, and because this is an AND, the 0 comes out. In this case, this 0 goes into this NOT gate and becomes a 1, and this 1 goes in not through a NOT gate, goes straight in, and becomes, so two 1s go into an AND gate, so therefore electricity comes out. So what are we doing here? We're actually having all four combinations. Two of them run through a NOT gate. Here the upper one goes through a NOT gate, but not the lower. Here the lower goes to a NOT gate. The upper one does not. And then here, they both go in unchanged. And that gives us the opportunity to decide which one of these four lines we're going to turn on. So we can, based on the inputs we put here, any one of the four lines can be turned on. It's our choice. We have four possibilities. Okay, so when you go and write code, Java or C++, you're writing code like A equals 5, B equals 6, and then later on you might want to use A and B. So the computer has to somehow record the values somewhere. And we use, because we're human beings, we have 10 fingers, so we use decimal numbers. But the computer can't record decimal numbers, it can only record electricity or not electricity. So what we'll do is we'll convert the decimal 5 into a binary 5. And remember from our first day of class, we said that that was 5 in binary. And we'll try to record that. So how can we record bits? How can we say, I have a bit, this one is a 0, this one's a 1, this one's a 0, this one's a 1. We want to record that and do it in such a way that if we record it and come back later, the value will still be there. That's what we want to do. So it'd be nice if we had some kind of an electronic gadget that has, it would have to have two inputs. So it would have to be one input to set it to the value we want to set it to. Because we're going to do two things. From time to time, we're going to set the value. And then we're going to also say, okay, whatever I just set it to, freeze that because I need it later. So we'll have one input where we can set it to a 0 or a 1. And then we'll have another input that says, okay, I'm either setting it or I'm freezing it. So I call this input like a set and a freeze. So now our goal is to design what's in the cloud. So this would be a good piece of electronic equipment to have, because now we can record 0s and 1s and then freeze them for later. Okay? And this will end up being computer memory. So this was, I think, back in the 1940s. Someone came up with the idea, if you take a NOT OR gate, and what I did was I put this, you usually see the circle right in front of it, I slid it over a little, just so it would be a little bit more clear. So the circle means the value gets flipped. So this piece of equipment takes a NOT OR gate and another NOT OR gate, and they each have two inputs. And the output of one NOT OR gate is fed into the other, like the sister NOT OR gate, fed into the other one. And the output of this one gets fed into this one. So now we have to kind of follow what's going on. So suppose we had a 0 go into here. So what we control is this one and this one. These two inputs are really the outputs of the stuff that's in the cloud, right? So if we set this to 0 and this to 1, let's follow this one. This 0 running into this OR gate means the output of this OR gate is going to be what?
1.
What? Well, okay, it could be 0, 1, or you don't know. So, right, those are the three choices. Well, hold on, let's do one that we do know. I'm kind of giving away the answer. If this is a 1, and this is something we're not quite sure of, because we only control these two. If this is a 1 and it goes into an OR gate, the output will definitely be 1. Because an OR gate, all it needs is one input, and bang. So one of the transistors is on, and the other one may or may not be on, and who cares? The electricity will flow through to the bottom. I'm sorry, the electricity won't flow through the bottom. So the output of this OR gate will definitely be 1. The output of this one's a little questionable because, and don't go by what I'm drawing here, if this is a 0, what is the output of this OR gate? Well, it's whatever this is. Whatever that is, right? And we don't control that. That's coming out of here. So once we let this electricity flow into this OR gate, which comes out of the OR gate, then goes to a NOT gate, and then goes out of here and wires back into here, we have 2 zeros. Therefore, a 0 comes out of this OR gate, and it goes to a NOT gate. Now we have a 1, and this goes down to here. Okay? So, you might think, this is a lot of work, and what is it really doing for us? Well, if we set this wire to 0 and this wire to 1, the output will be 1 and 0. It'll just be the reverse of the inputs. Okay. Well, we could have just used 2 wires and had them crisscross, right? So, since this is symmetrical, it's the same idea. If you put a 1 here and a 0 here, just the outputs flip. So this is actually a 0 here and a 1 here. Okay. Now, there's 4 cases because we have 2 inputs, right? So we tried the 0, 1 and the 1, 0. Now we have a very boring case and we have a very exciting case. Okay, the boring case is if we put 2 1s in here, what will be the result? And the result will be 1s will come out of both of these because a 1 going into an OR gate, it doesn't care what the other input is. So the output will definitely be 1. It'll go through the 2 NOT gates, turn to 0, and the zeros get fed in on the other side. And so the 2 outputs will be 0. So if we set this to 1 and this to 1, the 2 outputs is 0. Okay, that's kind of uninteresting. Here's a very interesting case. So I'm using green to mean 0, red to mean 1, and then I'm just picking 2 random colors, and I'm asking you what are those colors. So if we set this to 0, and we set this to 0, what's the result? Well, this one being 0 means I need to know this one, right? Because it's an OR gate. And an OR says, if one of them is a 1, the output's a 1. If one or more is 0, if they're all 0, the output is 0. So the answer to the question, what is the output of this one? It's whatever this value is. But we don't know what it is, but maybe when we look down here, we'll figure it out. When this goes through, its output will be whatever this input is. Because 0 plus this one will produce that as output. When it goes through the NOT gate, the output here is going to be the opposite of this. But we don't know what the value is. Okay. So the opposite will come into here, and the output of this OR gate with a 0 and whatever this is, the output of this OR gate will be this input. And then when it goes through the NOT gate, it becomes the other value. And the other value comes into here. So it eventually settles. So what are these values? The blue and the magenta. Is that the name of that color? Magenta? Pinkish red? Or, okay. What are they? Are they zeros? Well, we know they're opposites of each other, but what are they? Zeros and, is this one a 1 and this one's a 0? Is this one a 0 or this one's a 1? So at the very moment I turn these both to 0, what's happening? So maybe try not to think one's a 1 and one's a 0. Just ask yourself, what's happening when I turn these to zeros?
This is the before value.
The value that was there before is the value that stays, right? Because if this would, let's say this means 1 and this means 0. If this was a 1 before, meaning I put a 1 here and a 0 here, let it flow through, that would go 1 here, 0 here. Now I set them both to 0. What does that do? It makes these two values freeze to whatever they were before. Whatever it was before, that just now freezes. So this is an interesting case. If we do an input of 0 and 1, it comes out reversed, 1 and 0. If we do an input of 1 and 0, again, it flips over. So we're kind of like setting the output. We control the output. The case where we put 2 1s in, that's kind of boring. Just 2 zeros come out. But this one, when we go 0, 0, we now have the ability to say whatever the value was, freeze it. So we could actually put, let's say, a 1 here, a 0 here, give it a little time for the current to flow through, and then go 0, 0. And now we froze the value that we set it to. So there's two things we can do. We can set it and we can freeze it. So now we'll get, this is basically the same picture. It's this part we just saw, and now I'm putting an AND gate in front of it. And what we're going to do is we're going to build a piece of electronics that we can set the value and then freeze the value. It's going to be 2 steps, but we're going to be able to set the value and freeze the value. So if I make the input coming in through the top a 0, and the input coming in through the bottom a 1, then it's kind of like I'm saying I want a 1 to go up here and a 0 to come out of here. And what I've also done here is I've taken the picture from the last frame and I've kind of chopped off. Remember we had 2 outputs? Well, the output, as long as we don't do a 1 and a 1, the outputs are always opposite of each other, so we only need to remember one of them. And the one that comes out the bottom is the value that went into the top. So we'll have 2 inputs, we'll have an input up here, and then a value coming out of here. So if we set this input to 0, which then makes this input turn into, this not turns it into a 1, and this input is set, that means we are allowing input to go into this piece of electronic equipment. We're allowing input in. If we do that, we've now set this output to 0. And if we started playing with this, if we started changing to 1 and 0, this thing's going to start a little bit later, start changing too. But if we set this to 0, and we set this to 1, meaning accept input, then later on set this one to 0, this 0 going through these 2 AND gates shuts off both AND gates and we have zeros going in. And what we said was zeros going in means the value froze. So if we do step 1, a 0 and a 1, give it a little time, right? We give it a little time, and then, what I mean by give it a little time, allow this electricity to flow through to set this value, to have everything all set. Then turn this one to 0. Then the value we set it at, when we turn it to 0, will be frozen. Now what happens if we start playing around with this one? Well, it's ignored. The reason it's ignored is because this is set to 0 and puts 2 zeros into here, and it just ignores the input at that point. It's frozen. Okay. So, and then, here's how we can set the bit to a 1. We set this value to 1, meaning accept input. We set the input value to 1. This 1 comes through here, which makes a 0 come through here. And therefore this 1, they flip-flop. This goes on, the output is 1. We've chopped off this output. So we're setting this piece of electronics to a 1. And then we're setting this value to 0, and once again, the value here doesn't matter. Once we've turned it into memory. Okay, so now suppose we have 4 of those things we just saw, 4 bits of memory, meaning the 2 flip-flops feeding into each other and the ability to set them. What we can do is, and this is now kind of like that decoder we saw before. Suppose we have 4 bits of memory, and their values are A, B, C, and D, meaning A could be a 0 or a 1. B could be a 0 or a 1, C could be a 0 or a 1, and a D could be a 0 or a 1. And then suppose we had another piece of memory sitting over here. And for some reason, we wanted to take the contents of one of these 4 bits, right, and copy it somewhere. So that would be like when you say in your Java code, A equals 5. All right, so we're going to turn it into binary. We're going to set a bunch of binary bits, and then we're going to save it. And then later on you say B equals A. So now we have to copy the contents over to somewhere else. So we have to say which one do we want to copy and where do we want it to go. Well, what we can do is, as long as we have powers of 2, our memory is organized in powers of 2, we can connect a decoder to decide which one we're interested in. Right? A decoder was a piece of hardware that if you put a value here, it'll tell you one and only one of the 4 possible outputs. And if we had 3 bits, it would be 8 outputs, and we turn one and only one of them on. So, in this example, I set the decoder value to 0 and 1. So 0 comes up here, and runs into here, that's a 1, and this 1 comes up here, runs into this NOT gate, and becomes a 0. So since this is now a 3-input AND gate, and we said it's very easy to make 3 input and 4 inputs, right? We just call the factory and say we need a 3 input, we need a 4 input. Since one of these inputs is a 0, because of the way we set this, a 0 is coming out of here, right? If we set this to 0 and 1, then this being a 0 gets converted into a 1, and this being a 1 stays a 1. So we have 2 1s going in. Okay? So what's the output of this AND gate? Well, we have this is a 1, this is a 1, and what's this one? Whatever B is, right? We don't know what B is. But B is coming out of here, so I changed it to blue, meaning, well, I don't know what it is, a 0 or a 1. But the output of this gate will be whatever B is. And then based on these 2 settings, like we say, we have all 4 combinations. So by having this a 0 and a 1, this 0 goes straight into here, which kills this AND gate. So a 0 comes out of there. And then this 0 here also kills this AND gate. So this 0 shuts both of these off and leaves both of these on. And this one shuts this one off and leaves that one on. So 3 of these values will not go into this 4-input AND gate. 3 of the values will be shut off, and the last one will be whatever its value is. And it's all going into a 4-input OR gate, which we also said is easy to build. So, by setting this value to 0 and 1, and allowing a little time to go by, the value of B showed up here. Now, I'm assuming you understand, we're going to set the bit on that receives the value. Give it a little time to get there, and then shut it off. So it'll remember B. So it's going to be 2 steps. Actually, there's 3 steps to doing this. One is pick the place you want the value from. Let that electricity be set. Then allow B to flow through to get to this location. Once it gets there, then freeze it. So this is really like addressing memory or memory transfer. Okay, this picture may look very clumsy, but all it is the previous picture times 4. So now what I'm doing, have you ever heard the expression a nibble? We've heard of bytes. Byte is 8 bits considered together, right? Have you ever heard of a nibble, or have they stopped using it?
4 bits.
Right, okay, 4 bits, I have a byte. Okay.
Yeah.
So what I'm doing is I'm taking data and I'm grouping them together in sets of 4 bits. And so here's the 0 set, the 1 set, the 2 set, and the 3 set. And once again, we have a decoder. So now we can pick which of the 4 sets we're interested in. So if I put 0, 0 here, this line is on and these 3 are off. This line being on turns on all of these AND gates. And the values of these 4 bits get ANDed with this line that's on. So the values coming down here are what? Whatever these are, right?
Yeah.
Now, the decoder shut these 3 lines off. So this line being off, which goes into all of these AND gates, what values are coming out of these AND gates? Zeros, because this line shut them all off. And same here, this line shut off all 4 of these, shut off the whole nibble. And then this line shut off this whole nibble. And then all of these outputs of all of these gates, they all get dumped into an OR gate. So this first OR gate is 0 or 0 or 0 or whatever A was. So what eventually will happen is A will show up here. Right? And B will show up here, and C will show up here, and D will show up here. Okay, so what we can do is we can pick which one of these four we want, and then they'll show up over here. Obviously, we would have to have some hardware here that sends the inputs to 1, allowing the value to come in, and then set it to 0 once we decide we want to freeze it. Okay, so the only difference between this slide and this slide is the decoder value. I'm sorry? The decoder value changed. So when I hit it, you'll just see this will go, these numbers will change, therefore the output of these lines will change, a different one will turn on, and then whichever one turns on, that's the one that shows up down here. So once I hit that, once I say I want 0, 1, which in binary is nibble number 2, right? This is the 0 nibble, the 1 nibble, the 2 nibble, and the 3 nibble. So now I want nibble 2. This line is on, this line is off, the decoder turns this line on and shuts the other 3 off. And then the values of I, J, K, and L go running into the destination, the 4 destination pieces of memory. So we're going to use the expression memory when we're talking about where you're storing stuff. And if you have a destination, this is going to be closer to the processor. We'll call that set of bits a register, a place where we're going to store stuff to do some basic mathematics. Okay. So we talked about how we can, we just showed how we can read from memory. And now we want to show how we can also write to memory. So suppose you said, suppose you had a line that said, like, A equals 5 and then B equals A. So the line B equals A, you might have to write A to a temporary register as one step, and as we now know, that takes several steps to do. Then take that value and write it to an area called B. So this diagram says, assuming we have 4 inputs that are already set by magic, they're already set, if we want to copy these values into one of these nibbles, into one of these nibbles, then what we can do is we pick the nibble, and this is, once again, this is a decoder, but we're now going to call this the memory address register, so it's the address we're writing to in memory. So that'll be the value of it. And the other thing is, if you think about it, a decoder will always have an output. One of its outputs will always be on, right? And there are going to be times where we want to write these 4 bits to one place, and there are going to be times where we don't want to write anything to memory. We just want to freeze memory. So one of the homework assignments is going to be to take a decoder and add an extra bit so that if this bit is on, it acts like a decoder, meaning one line is on. If this bit is off, it shuts off everything. So anyone have an idea what this bit would do with the outputs of the decoder? Okay, well, yeah, like I say, that's one of the homework assignments. I was hoping that was one of the easy ones. But anyway, so what we can do is we can turn this thing on, which allows one of these to turn on. And later on, we're going to shut this off, which will shut off all 4 of them. So by asking for the 0, 1, the number 1 nibble, which is this one, we're turning this one on. So now this is the line that says accept data, right? And this is the actual input value, so they're coming in through the side. Okay, so when we set this to 0 and 1, there's some electronics in here, right? Transistors and resistors. It takes a little time for the electricity to flow through. Eventually, this opens for input. These values are wired into all of memory. So the contents will go into here. These will be frozen because their input value is set to 0. So they'll be frozen. They will ignore these values. So I said that I'm showing here that the memory values were A, B, C, D. In this one I have E, F, G, H, or W, X, Y, Z. and then these ones are the values they were before. Do you know why I kind of put an or, one or the other? Because as soon as you set this, the old values are kind of getting washed away while the new values are coming in. They go through the flip-flops, and it takes a little time. So there's going to be a little gray area where it might be the old value, it might be the new one coming in. Okay. But then, once we turn this to 0, it'll shut off all of these, and then the new values, the W, X, Y, and Z, will appear here. So once we shut that off, the fact that this is a 1 doesn't matter because, like your homework assignment, this thing is going to dominate all, it's going to shut off all 4 lines. And now all our memory is frozen. Okay? So, so what we've kind of done at a high speed, and I know we talked about a lot of these little parts last class. What we've done is we've taken these AND gates, OR gates, NOT gates, we've wired them together in such a way that we can group memory together and transfer data from one memory location to what we're going to call a register, starting next week. And we could copy data from, this is also a register, we'll say, copy it to a location. So if you have a piece of code that says A equals 5, semicolon, B equals A, how do we do B equals A? Well, we have to take the contents of A and copy it we have to take the contents of, let's say this nibble was A, copy it somewhere, okay, in this case, this is A, copy it somewhere, then take this and load it back into a different location. So each of these, copying data from one nibble to another, that takes several steps. And then copying memory back to a different location, that takes several steps. Okay? Okay, so what we've covered so far is how to read and write from memory. Sound good? Read and write from memory. Okay, now can you write a computer program that, well, let me